Hi, thanks for coming to my talk. I am José Díaz Rohena. I am a developer at Ableton. I work on Live. I've been at Ableton for, I'm rounding up to 3 years. The Live code base is more than 20 years old. It's been around for more than half of my life. It's around 1 million or so lines of code. It was created through the labor of a lot of really talented, dedicated people. And despite this, it can be really hard to understand and really hard to change. To the extent that, as Anna, who so well introduced me, shared during an ADC23 keynote, we tried rewriting it and decided to stop rewriting it. It's what some would call a legacy code base. In a legacy code base, it can be hard to make even simple changes. For example, exchanging every instance of some classes for re-implemented modern versions. Today, I'm going to share what I learned doing exactly that. The experience led to me becoming a better developer with strategies for dealing with hard-to-understand code that can be applied to a code base of any size. So whether you're working on a small project, a small but destined to be huge project, or just got that dream job at a mid-sized audio tech company based in Berlin, Germany, I think that there'll be something for you here. I like to think about what I learned as my legacy survival strategies. There are ways that I split big, difficult problems into smaller, slightly less difficult problems, making them easier to solve. And I do this using the basic tools of our trade, the compiler, the text editor, and Git. I'll share them along with case studies of the problems I encountered during the refactor, during this work that led me to rely on them. So today I'm going to cover how leaning on my compiler combined with rigorous-ish note-taking helped me find a starting point and direction for the work. How I used Git to make it easier to figure out how to refactor hard-to-test code without having to think about how to make that code testable at the same time. And how I moved my working process out of my head and into the IDE and text editor to deal with a legacy system that I should have known about before starting. But first, some table setting. One of my favorite things about Live is the file browser. I like how easy it is to navigate through different samples, presets, instruments, whatever, without losing creative momentum. And I think it's actually one of the things that sets us apart from other DAWs. The browser, besides being pretty cool, can do at least 2 things. As you can see, it can retrieve and display file data pretty quickly and let you do stuff with it. One of the things you can do with it is organize the display of this file data as you like. And actually, we just announced Live 12, which has a new feature that, this is not an ad, but I wish I could have shown it here, but I didn't know when we were going to release it. You can also now tag files to have organization be easier. Live does this by caching key information about files in a database. There, it can be easily accessed and displayed by the browser. Mainly, we store things like file type, size, and modification date. These types of data apply to just about every file we handle. Some data, however, are only relevant to a small number of files. For example, some of the extra info we carry or that MP3 files carry. Most of our files, live projects, device files, AIF, right? They don't have an artist or an album or a name associated with them. So storing that kind of thing for all files in our database doesn't really make sense. We have another location on the database for this, where we can store this different kinds of information, whatever is relevant for a given file. Of course, we call this metadata. Big surprise. Our metadata system is supported by two types on the C++ side of Live's code base. Another surprise. The main one's called metadata. It's the in-memory representation of that extra information that we're storing in the database. Entries consist of a key describing the type of data being stored and values the data itself. Metadata delta is the other type that supports the system. We use it to describe changes that are being made to metadata in the system. Together, these types are used to get metadata from our file scanner and into the database, or out of the database and into the browser. So I was the main driver of a refactor that replaced our metadata types with newly implemented versions. And you might ask, well, some of you might ask why, right? The old system works, and some parts of it have been around for 14 years, right? Legacy code is indeed code that works. Well, we did have some good reasons. Our metadata types were implemented in the main live code base, and therefore had dependencies that made it impossible for push to use them. And it would make the push team's life a lot easier to be able to use this code. Making them usable by push necessitated a total rewrite of the system, or at least of the type supporting the system. This rewrite then was performed with the benefit of hindsight and C++ 17, with the result being easier to use and understand. Most directly, my team was working on a feature that needed to use these metadata systems. We knew that this new type had been implemented, and we didn't want to essentially waste time and money building our feature against a metadata API that we knew that at some indeterminate point at least was going to go away. The mandate was clear. Live uses what I'm going to be referring to as legacy metadata and legacy metadata delta objects throughout the code base. We need to change the use of these types with new metadata and new metadata delta types. In the code base, they're just distinguished by a namespace, so it's like it really is like one or the other. They have identical semantics, but some different naming conventions, and sometimes really greatly divergent API, which kind of comes into play near the end of the cases that I'm going to present. The changes, this is a refactor, right? Changes should preserve behavior. Ideally, the user will never know I was here. I need to deliver alongside with the refactored code a clean, informative Git history. It should be structured in a way that makes it easy to understand the changes being made to bring the code from the state it was when I checked it out from the main branch to the state I want to be checked in. And each commit needs to build. So I knew I was in for a challenge from having worked in live before, and this is kind of a recurring theme, what I didn't appreciate was how the sheer number of changes I would have to make would multiply the difficulty, or not just multiply, it was exponentially, I guess, more difficult just to make up an amount. And here's why. So this is the actual name of legacy metadata. As you can see, that's 822 results in the code base. And here's the legacy metadata delta, 469 results in the code base. So that's around 1,200 instances of this type, 1,000 of which are probably require actual work that's not copy pasting. I actually didn't do this before starting, which is probably why I started. And this is great sometimes, when you're in an organization and sometimes people just trust you and you say you want to do something and they say, go with God, So that's kind of what happened here. But I did have support. I wasn't alone, right? Mainly, it came from the engineers on the team responsible for Lives Browser. They were the most knowledgeable about the code that I would be changing, and at least for one of them had literally written the lion's share of it. The Abletons in the audience know exactly who I'm talking about, including the new metadata system that I would be implementing. These engineers were available to help explain parts of the code base that seemed especially confusing, and most importantly were the ones that reviewed my pull requests and sometimes offered really, really valuable perspectives and just straight up new implementations when they felt that I hadn't completely hit the mark. And then one final bit before we actually get to the meat of it. So the way I approached this work was, this isn't a works cited necessarily, but I guess books that I like. I was deeply influenced by working effectively with legacy code, which I'm going to actually talk a lot about over the course of the presentation. It inspired me. It made me feel bad. It led me to understand what I was doing in a different way. Similarly, a philosophy of software design, after reading it, it kind of permeated how I think about code in general, in terms, especially in the way that code complexity is talked about as related to the amount of mental effort that is required to do tasks in a certain code base. And that idea is kind of key to at least my personal analysis of why the techniques that I developed for myself worked. And I think refactoring is just neat. It actually made me think a lot and write a lot about the organizational aspect, about pitching refactoring projects and when and how you should refactor. That didn't actually make it into this talk, but it's still a great read. So without further ado, let's talk about the code base. Oh, there we go. So sorry. I didn't know you were seeing my cursor in my apps. Anyway, so starting the refactor, I didn't have a solid plan or direction, but I did have a requirement to, whatever I ended up doing, deliver a sensible Git history. Pull requests should be as small as possible and focus on one clear outcome. Commit should each only have one meaningful change and should be ordered in a way that makes sense. And each commit needs to build. This implies a few questions. How do I keep my changes small? And how do I keep my changes orderly? Or to rephrase, to answer, how do I keep changes small? How do I keep changes small while making sure each commit builds? And why would this be a challenge? We do a lot of what you see in this kind of contrived example here. A function, foo, will accept a metadata object. It'll do some stuff to it, and then it'll pass it along to bar, which it depends on. So because of this dependency, upgrading bar to use the new metadata type will necessarily break foo. Now, you could try to fix this by also upgrading foo's interface and completely using the new type in foo, but that is going to break whatever calls foo. And you can repeat this pattern until you've made 200 commits worth of work and in one commit, which again, we cannot do. I don't even know if it's physically possible or mentally possible to do this. I know that we wouldn't review it. The first thing I did then was define functions that converted from the old to the new type. A kind of scaffold that I could use to hold up the code while I made my changes. It's pretty simple, as you can see in the above example. After changing the metadata type that bar accepts, you can fix the build by converting the old metadata that foo gets into the new type. Cool, build fixed. That's what you commit. So how do we make small changes? Answered. Nice. How do we, however, make orderly changes? How do we even figure out what needs to be changed? You know, these types of functions occur tens of 20s of times in the code base, and it's not exactly easy to simply Control F and figure out what's going on. Of course, in a small project and in some files in live, it is pretty obvious. But the reality of a legacy code base, or I guess just a large code base also, is more like this. Who uses bar? Who calls me? I don't know. And also, bar might be named something super unhelpful that is actually impossible even to do a text search for. This is where we can, as described in working effectively with legacy code, lean on our compilers. It's a simple but super powerful concept, and you've already been applying it every time you mess up and it doesn't build. You make the change. You make an interface breaking change and you try to build. When it fails, the compiler will of course let you know where it failed. That's where you know your next change is going to be. That is the dependent that got broken. So combined with the conversion functions that I defined, I use this technique to work my way through the code, making small building changes. Doing it this way also took some of the effort out of creating a sensible commit history. Generally, it would go like this. I'd revise a function to use the new type and find its dependence by seeing what breaks when I try to build. Once I found those dependents, I would prop up the build with scaffolding code and commit my changes. Then I would go through the dependents that I just scaffolded and commit by commit, amend them to properly use the new type. Doing this reveals the next set of dependents that need to be upgraded. With the right starting point, I could figure out what needed to be changed while building a commit history that made sense without expending extra mental energy. I just needed to pick a starting point based on the code's dependency structure. Specifically, I needed to find the function or functions that have the types I want to change in their interface, but don't depend on any other such function. This would probably be close to where metadata are iterated through and read and their values written into the file database. If I started there, leaning on my compiler, following what breaks, would keep me moving in one direction. Towards the endpoint, functions that didn't have metadata types in their interfaces, but originated metadata objects and then passed them down into functions that did. And this worked for a bit, but I actually eventually felt like I was making a mess. This was because some functions had several dependencies that used the old metadata type. And these dependencies were sometimes hard to see because of the way that these functions were written. This can happen in a function that's complicated, really long, or complicated and really long. Consider bar that just got upgraded. Foo depends on it, so we scaffold it and commit the change. Now I think it's time to upgrade foo, and I start doing that. I expend, some time, some mental energy, and I realize in the middle of it that I've actually missed a dependency. I don't have a way of calling this new gas dependency because it still takes the old type. This is super annoying, and I know that in order to keep my commit history normal, easy to understand, dependency, set of dependency by set of dependency, I should address gas first. So I revert my changes and I fix it before continuing. This wasn't a total emergency viewed just in this instance, but it started happening enough that it felt like I started wasting time and kind of undercutting the benefit of kind of mechanically figuring out the refactor. So I ended up doing what I'd been trying to avoid, mapping the system out just by looking at the code. Doing this after I'd already knocked out some of the refactor with this leaning on the compiler, however, was a lot easier. This kind of code first, ask questions later exploration combined with note-taking quickly became one of my core working habits. I found it easier to think through hard problems or understand complex code when I can jot down my impressions or draw upside down dependency diagrams that are only half right. If it's laid out on the page, you don't need to expend mental effort remembering everything. So I made good progress with this breaking, scaffolding, and mapping pattern that I used in the first example. Eventually, though, I ended up a little bit stuck again and a little bit stressed because I ended up in a part of the code base that wasn't well covered with tests. It was also a part of the code base that happened to be especially hard to understand, to the extent that I couldn't really figure out what the functions in it were doing or who was calling them. Despite this, I got to work with my process, finding the points I needed to change, but with the added task and mental overhead of figuring out if any of the code had tests, and if not, how I would make the code testable. This was time-consuming, and I began to get stressed about doing this for every function I wanted to change. Near the beginning of the project, I didn't really think about this because the code coverage was great, and all I had to do was change existing tests. Now I had to think about it, and I was feeling bad because this was around the point where I'd started working effectively with legacy code. There, refactoring is described as setting up my interpretation is setting up a feedback loop that allows you to quickly and reliably validate your changes. Or I guess that's the precondition for refactoring. So what you do is you put the code that you want to refactor under test. Make sure that the tests pass. And then you refactor that code to your satisfaction until the tests can pass again. So this is a super powerful technique. One, as I pointed out, it gives you very fast validation as to whether the changes you made actually work, and it very readily communicates to people that are reviewing your pull requests or looking at the code sometime in the future that the new implementation doesn't just work as expected, but as it did before. An important thing there is, especially for complicated code, the behavior of the code might defy your expectations. I was really sensitive about this because I didn't really understand what was going on in the code. So I was super stressed, trying to figure out how to make these changes, how to get things under test, and then how I would create a Git history where those tests are implemented before my changes. I found a solution in separating the task of learning the system and refactoring from the task of figuring those tests out. And it's a very Git-heavy process that I used. So first I would forget about the tests. Check out a branch that I had no intention of merging in. And then I would apply the techniques that I described in my first case to incrementally make my changes, get to know the system, see what's going on. Then I would clean up the branch's history, everything in order, one change per commit, all that good stuff, everything builds. Basically, the result should be ready for review, besides, of course, the lack of tests. Now, with a tidy Git history, I had a framework for systematically checking test coverage. To do this, I would typically open up a draft pull request for this cleaned up exploratory branch and do code review on it. Take notes on to what extent the changes I need to be backed, the changes I made need to be backed by tests. Now that I knew what functions needed tests, I would start a new branch and implement the tests there, along with any preparatory refactors that I decided to do. Finally, I could cherry pick changes from this exploratory branch onto the branch with new test coverage. Using Git this way let me work in a more focused way, and it made the work a lot easier. The core issue here is that my whole approach was based on making changes and learning based on what breaks when I make those changes. And the approach started seeming incompatible with implementing the tests the way that I felt I ought to, since I wouldn't have the context needed to write those tests until after making my changes. This new pattern helped me resolve this apparent contradiction without too much extra mental overhead. It also generally lowered my stress. Some parts of the refactor, especially after this point, got very honestly confusing. And getting used to reviewing my changes early definitely helped me from losing the plot in a few instances. It felt like I had another layer, another safety net, I suppose, to help me collect myself. In my final example, I put together the strategies I developed over the course of the refactor to, instead of understanding a large part of the system, understand one comparatively small but hard to understand part of it, a parallel metadata system that I didn't even know existed. As in the previous example, this happened to me a lot. This is what happens when you kind of just go step by step and that is the one downside of all these methods, right? Of the way that I've been doing it. If you don't map out everything in advance, you can get surprises. So like last time, I was just cruising along and refactoring function by function and, learning how the system worked. And suddenly, what the heck is a serializable metadata? I knew that there was legacy metadata, there's legacy metadata delta, there's maybe some internal subtypes that I haven't talked about and mostly won't. What the heck is this? And what do I even do with it? This happened a bit late in the game as well, and it freaked me out, honestly, which is why I'm talking about it. So it turns out, several months later, I know what it does. It can do a few things for us. Whereas the types that I referred to earlier, that I introduced at the beginning of this talk, are meant for handling metadata on its way into or out of the database. This type is for writing metadata to file. And we use it to speed up PAX installation. There we go. It inherits from one of Live's main base classes. Here I'm calling it serializable. That's how it can, that's where it gets its ability to serialize data from. More on that in a little bit. It can be created with these in-memory metadata types, the legacy types, and soon the new metadata types, and it can also create them. So that's the point where I ran into it, where the in-memory metadata was having some things done to it, and then this serializable metadata is created, and then that serializable metadata is used to then serialize or write the metadata to file during PAX creation. And thanks to the patterns I had picked up over the course of the refactor, this part at least was not so hard. I realized pretty quickly, okay, in terms of the actual usage, no one cares about serializable metadata besides being able to interface with the in-memory metadata type. So cool, have it create the new metadata type and have it accept the old metadata type. But we weren't actually done. And here we go into implementation land, so I'm sorry for this. The code responsible for converting to in-memory metadata had a deep dependency on the legacy metadata system. Now, what does this mean? Legacy metadatum is an implementation detail of the old system. It's the actual object that a value is stored in. And there's a function that gets called when we create the metadata that is used in the rest of the system that has to return this type. And we don't want to use this anymore. The class that has that dependency is nested a few layers down into the composition of my newly discovered serializable metadata type. As you can see in red, it's owned by an item that's owned by serializable metadata. And I'm concerned because they all inherit from this serializable base class, which I don't know about. Besides hearing people talk about the class, reading a little bit on our wiki about it, I hadn't had to work with it. I knew that it might be picky about the composition of classes that inherit from it, which was super concerning because as you can see, my problem is kind of one of composition. I don't know, and I'm scared. Why would I be scared? Because I'm not sure if I'm about to break something. And if I do break something, how I'm going to find out. You see, Live has some core base classes that we need to inherit from when implementing new classes. They do things like allow our types to have reference counting or to be managed by smart pointers. You know, a lot of stuff that would maybe just be standard library implementations if the project were started now and not at the turn of the century. Many of these were implemented a long time ago, of course, so they themselves can be hard to understand just from reading the headers. They can have gotchas that can be hard to catch without just hitting them. For example, one of our base classes will, if you inherit from it, make it so your class has to be heap allocated using one of our pointers. It'll build fine, but you'll get an assertion at runtime when it's destroyed. Serializable, the class that all of these metadata classes inherit from, is one of these core base classes, and this is why I'm scared. In what ways does inheriting from this base class limit what I can do? Also, in what wild ways might I break things? As I said before, I have a hunch that the classes I just discovered may be picky about composition, which is concerning because there's a fundamental difference between how serializable metadata and the new metadata system store values. And this difference is tied to how the classes in both of these systems are composed. Here's a side-by-side comparison of how the old metadata system, and by way of that, my newly discovered parallel serializable metadata system store values next to the new way. So you'll see that each item in a serializable metadata container gets a key ID, which describes the kind of value, the kind of information that's being held, and then a list of those values, each of which, it'll be either functionally, it'll either be a list of integers or a list of strings. And on the right, here's the new system that has that same unique key ID per entry, but holds one value, either a list of integers and a list of strings. So how do you reconcile these two ways of storing the data? We have to figure this out in order to know how to get rid of the old metadata dependency, which is in a class that's in the middle of all of this. So this is a great place to start spiraling. Should I change serializable metadata's composition to reflect the internal composition of the new metadata type? Should the way they store values even be the same? Maybe we need a new design. I don't know. What can I even do though? I'm having all like these intrusive design, what's the right thing thoughts while not even understanding what I'm allowed to do without breaking everything. The surface area of the code I was touching wasn't as large as in my earlier examples, but I was overwhelmed all the same because I was trying to solve two questions at once, and I was having this discussion purely in my head. Things didn't start moving until I decided to pursue the fastest, easiest path to something that worked, and eventually wrote out that plan. So similar to case 2, first step is forget about doing it right or doing it properly. Focus on getting something working. Second, a lot of steps that are not, in their detail, are not incredibly relevant. But the point is that I needed to write a plan that gets me to a place where the code is no longer dependent on the old metadata system. That's the only thing that matters. Well, it's kind of the only thing. The other things that matter for this plan is that each step changes as little code as possible, and each step needs to build. This way I could get fast, reliable feedback from the compiler as to whether the general approach could work. If it works, great. I can write tests and refactor to do something nicer. This plan failed really early, which was great because I was able to prevent a lot of arguing in my head about what the right thing was to do, what the right thing to do was, and what might happen if I try things simply by trying something out. And I overall ended up in a nice loop where I would make my plan, try it, fail, and build a new plan with what I learned. Like before, I was learning more about the code by working with it, but instead of building that knowledge while mapping out a broad set of dependencies or a broad part of the code, I was iterating towards a deeper understanding of a smaller piece of code. So what did we learn? The strategies that I just shared with you helped me make good decisions about code, even while I was struggling to understand what it was doing and how it worked. I think that there, to an extent, an argument that it's really hard to understand a legacy system, much less design ideal ways of improving it without actually going into it and trying things and failing. I think that there's also an argument that a big part of the challenge of working with a big legacy system is the amount of mental overhead required. With the right habits, the work can be made less complex, and this is what we should be striving for. These observations don't just apply to legacy code. I'm thinking right now of a mentor at Ableton who pointed out to me that a common mistake people make when building something new is to try to get it perfect in one go. This doesn't make any sense. You get a lot of knowledge about the actual problem just by building something, even if it doesn't work. And the same, I think, can be said about legacy. So I started this talk saying that I grew a lot as a developer as a result of doing this refactor. And I framed that growth in terms of strategies that I employed to make the work manageable. And that's true. A lot of my growth is due to finding strategies that work for me. But I think I also grew a lot from just consistent exposure and engagement with this large commercial code base. I probably read more code in a small period of time than I ever had. I was presented with real-life cases of different design patterns and anti-patterns in a context that allowed me to really feel why certain things do or don't work. It's one thing to read about that code should be modular, and it's a totally other thing to have your life actively made a little bit harder because a piece of code isn't as modular as it should or could be. And I got to reflect deeply on design decisions while not having to make too many of them on my own, which is a real treat. All the while, I had support from super experienced people to basically check my work and keep me from straying too far from the path. Does it make sense to throw a junior engineer into a difficult, long refactor for their own personal growth? Maybe, if they want to. I think it's more that if you're part of an organization that has a big legacy code base, projects to refactor or otherwise improve that code base will inevitably come up. I want to suggest that this could be an opportunity for juniors if you're so disposed to do a lot of learning. Importantly, don't assume that because you weren't there from day one that you don't have something to contribute, and don't assume that it's better for someone else who knows more than you, who can do it faster, to do the work. It's actually, in my view, more up to the kind of support the organization can give to you to do this kind of thing. I'm personally grateful that I had the opportunity to do this project and that I was given space to see it through. And finally, this has been obviously a very organizational, corporate, environment type of presentation, but I don't think that these insights are available only to people who have access to this kind of commercial code base. And that's because I think a lot of what I learned didn't come down to those challenges that you associate with a legacy code base of being hard to understand or hard to change because there aren't enough tests, or things aren't I guess modern, whatever that means. But rather the challenge of diving into a new to you large code base. It's really the scale of the refactor that I think pushed me to the point of having to develop new strategies in order to effectively work on it. I'm mentioning this in case you're an indie developer or a hobbyist or a student and you find yourself wanting to immerse yourself in something really big. To that person, I would suggest maybe seeing if there are big open source projects that you can be a part of. I'm thinking specifically of things like the Surge synthesizer that is a really great product, really great synth, and iPlug 2, another great plugin framework. That both have really great supportive online communities. But that is it for me. Thank you very much.